Okay, we're back. This is basic statistics. We're looking at chapter 6. We're going to cover 6.3 and 6.4. So 6.3, sampling distributions and central limit theorem. So the average of all sample means from a population will be the same as the population mean. So you can take means of samples and basically use the same mean as the mean of the population. Standard deviation is a different case. If you have a sample standard deviation, it's dependent. It's not going to be the same as the population standard deviation. So what you're going to do is you're going to take, for the standard deviation, you're going to take the one from the population, so the one given by the population standard deviation, and you're going to divide it by the square root of the sample size. And now think about this. Why do we do that? Why do we use that for the sample standard deviation instead of the standard deviation of the population? Think about the ocean. Think about the varying sizes of fish in the ocean. It's all over the place, right? We got really tiny microbe fish, and we got huge fish. Sharks and stuff. Now, think of it as if I just took a sample from netting that I put around space in the ocean. Well, there'd be a lot less variability because the entire ocean has all these things, but just this, net that I have caging in whatever, sea life is there, it's going to be a lot less variation. So that's why we divide by the square root of the sample size. So the bigger the sample size, then the smaller the overall standard deviation gets. All right? Okay, so let's take a look. The central limit theorem on page 6. Look at the example. Suppose that general population of adult men has an average height of 70 inches, that's 5'10", with a standard deviation of 3 inches. What is the probability that a sample of 50 men will have an average of 72 inches, over 72 inches? Okay, so they want the probability that X is greater than 72. And so let's see what was given. What was given was N was equal to 50. Mu, the mean of the population is 70. The standard deviation of the population is 3. And so the standard deviation of this sample is going to be 3 divided by the square root of 50, which is going to be a lot less varied. So instead of 3, it's going to be 0.424. So much smaller than the entire population of all men. Obviously, a sample of 50 would be a lot less varied. All right, so let's take a look. First, we want to find Z. So remember how we find Z. We take the given minus the mean divided by the standard deviation, but we're going to use the standard deviation for the sample, not the population, 0.424, and that is 4.72. Let's draw ourselves a pretty picture. There's our standard normal curve, and Z is all the way up here, 4.72. So remember on our chart, that is, they want above that. On our chart, we look up 4.72, well, it stops, and so we just default to 0.99999. And so 0.99999, but that doesn't look like 99.9%. It's remember 0.9999 represents this area, so we're going to do 1 minus that. So it turns out that is not very likely at all. 0.0001. Not very likely that you're going to end up with average height over 72 inches with a random group of 50. All right. If you used Excel or even your calculator, it will give you something smaller than that. It gives Excel produces 0.00001216, which is fine if you want to use that. Like I said, I'll say it again on this video, I don't think using Excel for these really makes the problems a lot easier. I don't think it doesn't simplify them that much, and so I don't think it's worth it. I say just use your tables and charts. All right. So then 6.4, normal approximation for binomial distributions. And so that is a lot easier to find. That is just going to be, erase this for 6.4. So that's on the bottom of page 6. And we're talking about this. We have mu is equal to n times p, and sigma is equal to the square root of n pq. So the mean is just n times the probability, and the standard deviation is the square root times n times p times q. Remember, q is the probability it won't occur. P is the probability it will occur. So let's look at a couple examples. Suppose a weighted coin comes up heads 65% of the time. If it's flipped 300 times, find the probability the number of heads is between 200 and 250. Okay, so let's do that. We want to know the probability x is between 200 and 250. They gave us n is equal to 300. We would find mu by taking n times p. That's 300 times 0.65. That's 195. And then we would say sigma is equal to the square root of 300 times 0.65 times 0.35, which is the square root of 68.25, which is 8.26. All right. So we've got all of those. So because we're using continuous distribution for discrete values, we find, all right, so let's find our z-scores. So z for here, we'll call it z for 200. Oh, wait. That's why, wait, that was, I read that out loud, but then I didn't finish it. Because these are for discrete values, we're going to bump it so it includes the 200 and it includes the 250. So to do that, to include that in our set, we have to do 199.5 is less than x is less than 250.5. You see what we did? We're using discrete mathematics to figure out a continuous probability. And so to ensure that 200 is caught and 250 is caught, you just bump it down by 0.5 there and add 0.5 to that one. So when we find z, we're not really finding z of 200, really close, we're finding z of 199.5. So we do 199.5 minus 195 over 8.26. That gives us 0.54. So half a standard deviation above the mean. And then z of 250.5, that's going to be 250.5 minus 195 over 8.26. That's way off the charts. That's 6.72. 6.7 standard deviations above the mean. That's as high as it goes. So let's draw ourselves a pretty picture. And we want to find that probability for the z-scores. So when z is between 0.54 and 6.72, and so the probability of that, half a standard deviation above the mean is still going to be there. Almost 7 standard deviations above the mean is going to be as high as we're going to get. So on our chart, for that, we're going to use 0.9999, and we look up 0.54 on our chart, and that kicks out 0.7054. And now we just subtract those two, and so 0.9999 minus 0.7054 gives you this shaded area. So you got to figure 0.99999 was all the way down to the bottom, and then 0.754 was this area, so if we subtract them, that'll be the shaded area. So almost 30%, 0.2945. So about a 30% chance that it would fall between 200 and 250. All right, so let's do one more of these so you kind of get the feel for it. So if a certain slot machine contains wins 10% of the time, find the probability in 100 pulls it'll pay out more than 8 times. Okay, so you have 10 times, but we want to basically find 8, more than 8 times means we're going to find 9 or 10 or 11 or all the way up to 100. And so let's look at what we have. We have n equals 100. We have our mean is 100 times 0.10, so 10 times. That makes sense. These are pretty easy numbers. If it pays out 10% of the time and you play it 100 times, the expected amount of wins, or the mean, should be 10 times, right? That means the loss is 90 times, right? So when we are looking for the standard deviation, we take 100 times 0.1 times 0.9, and then to do the square root of that. So that's the square root of 9, which is 3. All right, so we want to know the probability. It's between 8 and 100. But we're going to bump this. We're going to make that 8.5. Well, wait. It was actually not 8. It was actually 9, right? Between 9 and 100. Because 9 or 10 or 11 or 12. So we want to... So we'll make that 8.5 to 100.5. And now we'll find our z-scores for that. So when I find the z-score for 8.5, that would be 8.5 minus 10 divided by 3, which is negative 0.5. That's convenient. And then for 100.5, that's going to be way up there again. 100.5 minus 10 divided by 3, 30.166. 30 standard deviations above the mean is ridiculous. So let's draw ourselves a pretty picture. Half a standard deviation below the mean is all the way down here. And when we look that up on our chart, that coincides with 0.3085. But that 31%, just talking about this little part right there, then all the way to the top here is z is equal to 30.16. That's going to be 0.99999. You don't really have to look that one up. And we want all the shaded area in between there. So if you just subtract those two, it is a likely scenario. But I mean, the question isn't really telling us much. What are the chances you're going to win more than 8 times? That leaves a lot. 9, 10, all the way up to 100. That's a lot. So it's going to be 0.9999 minus 0.3085, which is 0.691. So about 69% chance. But that is a 9, you win 9 times, or you win 10 times, or you win 11 times, or you win 12 times, all the way up to 100. So that's why that's so inflated. Okay. All right. Excellent. So that's chapter 6, 6.3 and 6.4. Next, we'll do chapter 7.